So, in this lecture we are going to talk about the theoretical basis for finite elements. So, in the last lecture we introduced finite elements, what is finite elements and how it is used for microsystems. Today we are going to establish the basis, mathematical basis for finite element analysis. So, we will revisit the definitions which we did in the last lecture. We will first define what is a mathematical model. Mathematical model is a set of algebraic differential or integral equations that govern the physical phenomenon of a particular system. The model could be based on set of assumptions. As I said, it could be based on geometry, kinematics, loads, boundary conditions, and also the restriction that is placed on the phenomenon and the laws of physics that govern it. So, in order to solve this mathematical model, we need a numerical model. We explained this in the last lecture. And a numerical model is an inexact procedure by which the governing equation can be solved for dependent variables or unknowns. So, any governing differential equation will have a dependent variable and an independent variable. So, what we are solving is for the dependent variable. The mathematical model, when it comes to that, is a problem being studied that must represent the physics consistent with the goals of the study. If you are talking about vibration problem, you have to solve a wave equation. If you are talking a electromagnetics problem, you have to solve a Maxwell's equation. And your goal of study in the Maxwell's equation is to find the electrical field, the magnetic flux, the magnetic field. In vibration problems, we are talking about deformation and deformation history. So, what are the desirable features of a computer for a mathematical model? The mathematical model must preserve all features in the formulation associated with the computational model. We should avoid any ad hoc approaches like the fixing approaches, or in other words, what we are talking about is to come up with a robust model that will physically represent the physical system. So, we will again talk about the physical system. So, we construct a mathematical model. A mathematical model will be either a boundary value problem having a set of governing equations and the boundary conditions, and also a initial value problem if it is a time dependent problem where you will have initial conditions at time t equal to 0. And these are basically obtained from the laws of physics like the conservation laws, energy laws, mass conservation, and also assumptions concerning the systems. So, we need a method to solve this mathematical model. So, we use numerical methods, and there are various numerical methods such as finite element method, finite difference method, boundary element method, etc. And these simulations cannot be solved by hand. So, we need a computational device such as computers to solve this. Let us take a second order system. The second order system is given by these equations here, which is essentially a ordinary differential equation where a of x or c of x are certain parameter that is spatially dependent, and this is also subjected to certain boundary conditions which is given by this equation. So, what does this equation represent? This equation represents many things. For example, it represents the elastic deformation of a bar, which is given here, where this P is the force, K is the spring constant that is here, and U is the deformation, and A is certain material parameter, which can be a modulus of elasticity. The same system can also represent the heat transfer in a bar, where P is the heat input or the heat output, and in the case of a bar, K is not present, K could be 0, and A is certain material constants such as the thermal conductivity and the area of cross section, and this is defined over a domain 0 to L. So, that has to be there. So, a physical system has a governing differential equation which is made from the certain basic unknowns. In the case of a bar, it is the deformation. In the case of heat transfer, it is the temperature. and it is subjected to certain boundary conditions as shown here. So, this is a physical system that we are trying to solve. Do we have an exact solution? Probably yes, but here what we are trying to see is how we could possibly use numerical methods such as finite element method to solve this problem. The same equations can also represent many things. Heat exchangers in a fin, where instead of A we have K times capital A, which represent the certain parameters of the heat exchanger. It also represents the flow over a viscous fluid, where A is basically viscosity in fluid, and the right hand side, the forcing function, is basically the density and the acceleration due to gravity. And both these equations again are set of boundary conditions, where in this heat exchange problem the temperature is preserved. We have a T at a certain spatial distance is specified, and its a heat flux is also specified. So, we see that a governing equation has a domain, and over which we need to solve, subjected to certain type of conditions called the boundary conditions, and all these equations are called the boundary value problems, for which we are seeking a solution. And in this problem, t is the dependent variable and x is the independent variable. So, what we are trying to solve is the dependent variable is the basic unknown for which we are looking for the solution. So, now let us actually define what is an exact solution and what is an approximate solution. An exact solution is the one that satisfies the governing differential equation at every point in the domain 0 to L, and also in addition it also satisfies the boundary conditions on the boundary. An approximate solution satisfies the differential equation as well as boundary conditions only in some acceptable sense and only at certain points. So, the goal here, what we are doing is not the exact solution, we are trying to seek an approximate solution as a linear combination of certain functions coupled with certain unknown coefficients called Ci. So, we are looking like a solutions which is given by this, which is basically sum of Ci into phi of x, and this is the function we need to choose appropriately such a way that it represents very nearly the exact solution, but not the exact, it is not the exact solution. So, if you plot this variation, what we are looking at is the difference between an exact solution and an approximate solution, which is shown here. The dotted line is exactly the approximate solution, which does not fall exactly on the exact solution line, but it is more or less very near the exact solution. We should note that approximate solution must contain unknowns to be determined, subject to satisfaction of the differential equations or the boundary condition. Of course, if we do not have unknowns, we have nothing to determine. Suppose u of x is an approximate solution to small u of x that we define for the differential equation. It will not satisfy either the differential equation or boundary condition exactly, and the solution depends upon the function we choose phi of x. If phi of x is selected such a way that it satisfies the differential equation exactly, then such a solution is called the Trapeze method. In the Trapeze method, the boundary conditions are not satisfied exactly, but only in approximate sense. Let us look at the second possibility. Suppose we choose phi of x which is satisfying only the boundary condition exactly and does not satisfy differential equation exactly, but satisfies only in some approximate sense, and such a solution is also an approximate solution. And most of our variational methods are based on this, because it is easier to choose a function that satisfies the boundary conditions rather than the differential equations. So, most of our methods that I am going to describe in this lecture are based on the premise that we choose the functions phi of x such a way that it satisfies the boundary conditions exactly and differential and the governing differential equation in some approximate sense. Let us revisit the same equation now. Suppose we choose some phi of x as a summation of the linear combination of this phi of x as the solution, and we substitute this into this equation. Obviously, this will not be satisfied exactly, because we already said that we are choosing phi of x that satisfies only the boundary conditions exactly, but not the governing differential equation. So, this will result into some residue which we call as R of x, because it will not satisfy exactly. So, our objective is to choose the CIs in our summation such a way that the residue of x is minimized or goes to 0 in some sense. So, now let us talk about how do we determine the approximate solution. In one sense, we can take this residue which is a function of all the CIs, the unknown coefficients, and we can selectively choose at the number of points and make it 0. So, we will get a set of simultaneous equation in terms of CI which we can solve and find the solution. This way of determining CIs is known as the collocation method. So, this is one of the numerical methods that we can actually do. So, the number of points we choose to make this residue go to 0 is equal to the number of unknown CIs we have in the solution. So, if there are 10 if it is 10 CIs to be determined, we need to choose 10 locations where this residue goes to 0, and such a method is called the collocation method. Is there any other method? Yes, there is other methods that you can construct. One way of doing is make this residual R of x go to 0 in some least square sense. That is, we minimize the integral of the square of the residual with respect to the unknown coefficients CIs. So, we take this equation, we call this J, which is nothing but integral of the domain length, which the integrand is r square, that is the square of the residue. So, we minimize this 0, that we take this integral, differentiate with the unknown coefficient Ci, and we get this. So, if we make this r into dou r by dou Ci equal to 0 over the domain, we get a set of n simultaneous equation corresponding to n CIs that we are trying to find out. Such a method of determining the approximate solution is called the least squares method. There are many methods that you can find, and one of the methods what we talk about is the weighted residual method, where we take the residue r, weight it with a weighting function psi, integrate over the domain. Okay. There will be n psi's corresponding to n unknowns, and these psi's are essentially the ones which satisfies the governing boundary conditions. So, this method is called the weighted residual method. We obtain n algebraic equation corresponding to n unknown c's. So, in general, the CIs are different from phi's. Phi's are basically the functions that are used to approximate the dependent variable that for which the solution we are trying to find out. Psi's are the ones which are the weighting functions which we are trying to use to find out the approximate solution. And in general, psi's and phi's are not same. If psi's and phi's are not same, such a method is called the Petrov-Galerkin method. If psi i's are same as phi i's, it is called the Galerkin method. Or in other words, we would see later that Galerkin method is another form of finite element methods that we are going to talk about in this course. So, we come back how we actually approximate the solutions in the finite element. We use what is called the Ritz method. So, Ritz method is the one in which an integral expression that is equivalent to a differential equation and natural boundary condition is minimized, because physical principles such as minimum total potential energy is the basis for this minimization, and for most problems of this curve, the quadratic functional to be minimized is constructed from the so called weak form of the solution. We will explain this a little later. So, the quadratic functional what we describe for the differential equation we just dealt with it is of this form. Okay. So, basically by minimizing this functional equal to 0, we get a set of n equations corresponding to n unknowns, which we solve to get the approximate solution. So, basically what we have done is we have taken the original equation and converted into this form, weak form of the equation. We will let you know in a little part a little later in the lecture. I will tell you how we can construct the weak form of the solution, and this is the method we adopt in FEM rather than taking the weighted route. So, let us summarize what we have understood now. We seek an approximate solution in the form of a linear combination of known functions that satisfy only the boundary conditions and unknown parameters that are determined to satisfy the governing equation in some approximate sense. There are several ways one can make the residual or the error due to approximation of the differential equation to 0. If the error is 0 at every point of the domain, then we obtain an exact solution. However, this is not the case. If the error is made to go to 0 at selected points n, it is called the collocation method. The residual can also be made to 0 in the least square sense using the least square method, and these are the various ways of making the residual 0. And by the method by which you use this to make the residual 0 takes a different forms or the different names or different numerical methods, as we discussed. So, this is summary. So, everything can be explained under the weighted residual method. So, you take the residue R, you weight it with the function Wi, integrate over the domain to 0. And there are n number of weights corresponding to n number of unknowns that we are trying to solve. If the weighted function is same as the approximation function you use for the dependent variable, such a method is called the Galerkin method. If the weighted material, if the weight is totally different from that of the approximation function, such a method is called the Petrov-Galerkin method. If the weight you use to minimize is equal to a direct delta function, which is called the collocation method, and if the weight is used as the differential of the residue with respect to the coefficient, then such a method is called the least square method. So, each of these are derived from one method which is called the weighted residual method, which basically takes some weight function, weight it with the residual, integrate over the domain. So, this is a fundamental principle for all the methods, and a finite element is one subset of this, which is got from the taking the weak form of the solution. So, we will come back to the variational principle. One of the fundamental principle that governs the systems is the principle of minimum total potential energy. The total energy is the energy due to the external forces acting on the structure and also due to inertia, which is called the kinetic energy. If you take the total energy and minimize with respect to unknown coefficient C equal to 0, then we get what is called the weak form of the solution. So, for example, for the problem which we just discussed, a second order governing differential equation, the weak form of the solution is obtained by this. So, when we minimize this equal to 0, and such a form is also called the weak form. So, how do you construct the weak form? We will let you know now. So, before we understand what is a weak form, let us talk about what is FEM. I discussed this in the last lecture, I am going to revisit here. The whole domain is characterized by 3 basic features. So, the first feature is the domain of the problem is represented by a collection of simple subdomains called the elements or the finite elements. The collection of these finite elements is called the finite element mesh. Over each finite element, the physical process is approximated by functions of desired type. The most common type is the polynomials or few other types, and the algebraic equations relating the physical quantities at selective points called nodes of the elements are developed. The element equations are then assembled together using the principle of continuity of the dependent variable and its gradients, or the balance of forces of physical quantities. Some of the FEM terminologies. What is an element? An element is a geometric subdomain of the region being simulated with property that it allows a unique derivation of the approximation functions. A node is a geometric location of the element which plays a role in derivation of the interpolation function, and it is the point at which the solution is sought. So, we do not, because even though what we are talking about is a continuum, we seek the solution only at nodes. Mesh is a collection of elements or nodes that replaces the actual domain, and the fundamental thing in FEM is writing the weak form of the equation. Weak form is an alternate statement of equilibrium. What we are looking at, a solution, exact solution is solving the governing equation. The governing equation is not amenable for solution. Weak form is amenable for numerical solution. It is an alternate statement of equilibrium. So, we take this domain, an approximate domain in FEM. This is the given domain. We mesh it. This is the meshed region into number of elements, and if we isolate as that typical element, we have the boundary fluxes, the loads because of the external tractions that are applied onto the boundary, that will be part of it, and we solve for each of this, synthesize the whole thing and get the solution at these nodes. So, these points are called the nodes, these points are called the nodes, and this is a typical element. So, we take each one of these, fit the approximate function, develop all the mathematics concerning this element, assemble this whole region and get the solution in terms of nodes. That in essence is what we call the finite element or finite element discretization. So, what is a finite element model? A set of algebraic equation relating the nodal values of the primary variable. Here we have said displacement. If it is a heat transfer problem, it is temperature. It is an electromagnetics problem, it is either electric field or a magnetic field or both. So, a set of algebraic equation relating to the nodal values of the primary variables to the nodal values of the secondary variable. The secondary variable can be forces or the heat flux or the magnetic flux, etc. It depends upon the problem. What is a finite element model? Finite element model is not same as the finite element method. There is only one finite element method, but there can be many finite element model. The one model could be based on least square finite elements, one model could be based on Galerkin finite element, etc. And the numerical simulation is the evaluation of the mathematical model, that is solution of the governing equation using the numerical simulation tools like FEM using a computer. So, the major steps in finite element model development, we begin with the governing equation of the problem, and the problem is converted into a weak form of the governing equation, which is an alternate statement of the equilibrium. We can use weighted residual statement or weighted integral statement for developing this. We solve the system, approximate solution, find the approximate solution, obtain the relations among the various quantity of interest over each element. So, we will come back here to this problem again and develop the weak form of the solution. So, this is a problem which we explained before. It can represent either the elastic deformation of a bar or a heat transfer in a bar and many more physical phenomena what you are thinking about. The system is same, the mathematics is same, the physics of the by which this equations was derived is totally different. So, here we are looking at the obtaining an approximate solution. So, if we want to take the whole domain as such, which is very long, so the approximation for such solution requires very higher order approximation. So, we need to actually suppose if this varies like a highly like a spline or a nerve like a variation, we need really a higher order approximation of the variable. So, maybe we need a 5th order polynomial or 7th order polynomial to get the variation over the entire domain. On the other hand, we split up this into many subdivision as we talked about in our first lecture on FEM. Then it is possible to use lower order approximation over this region. So, if we use many such elements, we can, even with a lower order approximation, we can simulate the actual variation more exactly. So, that is the philosophy by which we split up the entire domain into many subdomains called the elements. So, a typical element is shown here. So, a typical element will have the dependent variable, it can be u can be displacements or the temperature etc. as the case may be, and it is subjected to boundary fluxes which are called Q naught and QA and QB at the two ends at x equal to XA and x equal to XB. So, these are called the end forces or the heat as the case may be if it is a structural mechanics or the heat transfer problem, and the domain length h is basically XA minus XB, which is the length of the element. So, how do we get the weak form of the solution? So, the weak form of the solution is basically got by taking the governing equation and weighting it with some function w of x and integrating over the domain. So, in doing so, we have to integrate this by parts. So, while doing so, we can take that this while integrating by in most of the weighted residual technique or in the variational statement, integration by parts is an absolute necessity to get more insight into the system. So, we can actually do that by taking the, so here w is the first function and this quantity is the second function. So, we can choose this as a first function and this as a second function. So, when we integrate this is the first function and this could be the second function. So, when we integrate this, you take a du by dx first function into integral of the second function, which is given here, which is evaluated at the domain xa and xb, into differential of the first function, that is dw by dx, and these are grouped together. So, this statement has lot of meaning. This is the boundary term that is coming here. Let us take a brief look at what are the boundary terms. So, the boundary term says w evaluated at xb and into this flux term that is evaluated at xa, and w evaluated at xb and the flux term evaluated at xb. So, basically you see that there is a w term and a derivative of a u term. The derivative is basically a flux term which we call it as forces or heat flux, as the case may be depending upon the problem you solve, and a set of equations in this form. Okay. So, as I said earlier, A du by dx could be thought of a force input at xa and a force output at xb, or a heat input at xa or a heat input at xb. So, these are the boundary terms, and by doing this variational form, by weighting it with a function, we always get the form that this flux input takes in relation to the dependent variable. So, let us examine these boundary terms. The boundary terms was w into A du by dx. Okay. So, here we consider this A du by dx as a secondary variable, and this is obtained by integrating the actual governing equation by parts. The expression always contains the weight function w and a coefficient that depends upon the dependent unknown. In this case, the dependent coefficient is A du by dx, this is A du by dx. We will term the coefficient as a secondary variable. The weight function w in the boundary term, when replaced with the dependent variable u, becomes the primary variable. So, you see that the boundary term contains both the primary variable and the secondary variable, which is a derivative of the primary variable. And it is very necessary to understand this primary and dependent and the secondary variable, because these form the boundary value problem for which we need to solve, we need to satisfy our assumed solution exactly. So, because we said that the fundamental principle on which FEM is based is how we satisfy this equation exactly, the boundary conditions exactly. So, the primary variables and secondary variables always appear in pairs. They are like cause and effect, that is, one is a result of other. For example, u is the result is a deformation which is caused by A du by dx, which can be a heat or a force. So, they always occur in pair, and if there are more than one boundary expression resulting from the integration by parts, all like terms should be combined before identifying the primary and secondary variable, as we have done here. So, that we get the form of the secondary variable, which is very crucial for us in our finite element developing of the finite element approximation to the problem. When there are two or more independent boundary terms, that is, when each term contains a weight function w in different form. For example, if we are talking about the fourth order system such as beam, you would get the boundary terms of this form, where you have a primary variable in w and dw by dx, and a secondary variable which is second order and third order, as shown here. Then there will be two primary variables and two secondary variables for this problem. However, in the present model we have only one pair of primary and secondary variable, that is u and A du by dx. So, what are these primary and secondary variable? Do they have any meaning, physical meaning? The answer is yes. The primary variable essentially prescribes what is called the essential boundary conditions. In mathematical term, it is called the Dirichlet boundary condition. The secondary variable, which is like a cause and effect, as I said, it is caused because of the primary variable, which is basically a derivative of the primary variable, is called the natural boundary conditions, or in mathematical terms it is called the Neumann boundary conditions. So, in the following case, specifying u or du by dx is an essential boundary condition, and specifying A d square u by dx square or A d cube u by dx cube is the secondary variable. So, in the case of beam, each has a physical meaning. A d square u by dx square says it is a bending moment, and A d cube u by dx cube specifies it is a shear force. So, by taking the governing differential equation and weighting with a function and integrating by parts, we get a set of boundary terms, and these boundary terms has physical meaning, and they are essentially the essential boundary conditions or the natural boundary conditions. So, let us recall that the primary and secondary appear in pairs. One may specify only one element variable of each pair at a boundary point. Thus, we have A u and A du by dx is a pair. So, either only u or A du by du or never both may be specified. That is, when u is specified at a particular boundary, A du by dx cannot be specified, or if A du by dx is specified, u cannot be specified. Both cannot be specified simultaneously. So, thus for a problem what we have just considered, a second order problem with two boundary points, there can be 4 combination of boundary points. That is, when u is specified at x equal to 0, or u is specified at x equal to L, or u is specified at x equal to 0 and the flux is specified at x equal to L, or the flux is specified at x equal to 0 or u is specified at L, or only flux is specified at both the points x equal to 0 x L. So, there are 4 possible boundary conditions that you can see. So, now this equation is basically the weak form of the equation, and in the calculus of various terms, this is basically called the inner product, which is represented by B of W and U. It is the inner product between W and U, and these are the flux terms or the force terms. So, basically the variational problem is you take the inner product or the weak form of the equation is equal to L of W, and that is the variational statement of the problem that we are trying to solve. Now, we revisit our theorem of minimum potential energy, where we wrote a functional which is called the energy functional, which is nothing but the inner product of u with u. That is, when W is replaced by u, we get this is the inner product. So, when we minimize this inner product, we get the weak form of the solution. So, essentially you can convert. So, here we can see we adopt this for FEM and how this is related to the weighted residual technique. So, in summary, we could say that we take a quadratic functional which is in the weighted residual statement and replace the weight function with the dependent variable, we get the quadratic functional. Minimization of the quadratic functional is essentially the problem we are looking for, and that is an approach we take it for finite elements. So, the finite element model essentially uses this, converts the governing differential equation into algebraic equation. We will go through this motion little later, how we can construct these elements like stiffness matrix and the force vector from the governing differential equation as we go along. Here we are trying to establish only the theoretical basis of it. Let us take some examples here. So, consider a differential equation. This is a differential equation with constant coefficient with u as the dependent variable and x as the independent variable. It is subjected to 2 boundary conditions, that is u at x equal to 0 and u at x equal to 1 is 0. There is no need for an approximate solution here in per se, mainly because the exact solution exists and the exact solution is given by this term. Now, what we will do here is we will pursue the approximate solution for this method using the weighted residual technique by choosing different weights and see what kind of different numerical methods we can construct from this weighted residual technique. So, let us see how we can construct finite difference method, which is a very common method used for solving the differential equation. So, we now choose, the first thing that we need to choose is an approximation to the solution. So, we choose the approximation to the solution as given here. The question is why we have you choosing quadratic, because there are 3 points at x equal to 0, x equal to n, n minus 1, n and n plus 1, which is located at 0 and minus L and plus L. So, the first thing is we need to relate this approximate solution to the nodal displacements or the nodal quantities un minus 1, un and un plus 1, which are located at minus L, 0 and L. So, we substitute at x equal to minus L, the quantity is un minus 1, at x equal to 0 it is un, at x equal to minus L it is un. So, when we plug this into this equation 1, we get a relationship between the unknown coefficients and the unknown coefficient a0, a1, a2 with un minus 1, un and un plus 1. So, that is we can get the your a0 will be un, a1 will be given by this and a2 will be this. So, we plug it back here and we can write the u component as some functions phi I into ui, which is un minus 1 into phi 1, un into phi 2 and un plus 3 in phi 3, where phi 1, phi 2, phi 3 are given by this expression. So, let us look at the property of this. When we substitute x equal to minus L, we see that phi 2 and phi 3 goes to 0, but phi 1 exists, which is equal to 1. When x equal to 0, phi 1 and phi 3 are 0, phi 2 is equal to 1. And when x equal to L, phi 1 and phi 2 are 0 and phi 3 is equal to 1. So, it shows some property. Later we will see in FEM terms these are called shape functions. So, now we take the derivatives, the second derivative, first derivative. The second derivative is given by this, which is nothing but the finite difference approximation using central difference. So, this is called the central difference, the central difference to the problem. So, when we plug this back here, we take the error in the function. The error in the function is given by this when we plug this approximate solution to the governing differential equation. Now, we choose direct delta function as the weight function. When we choose the direct delta function as the weight function, that is we assume the weight functions of this form, okay, and each one of these functions, there are 3 unknowns are there, un minus 1, un and un plus 1. So, there are 3 weight functions. The weight function should contain 3 different functions, that is 3 direct delta functions are considered here. We weight each one of these with the error function as shown here and we get a set of equations. So, when we do that, the governing differential equations can be reduced to this form. This is basically the finite difference approximation for the given differential equation. So, we can derive the finite difference method from the weighted residual technique. Let us now consider the method of moments. Again, we will take the same equation for which we have shown that there exists an exact solution. The same domain u is u of 0 and u of 1, where is the domain length is 1 and at the boundaries the dependent variable goes to 0. And now for this we need to choose a weight function, and the weight function is taken as the increasing order of polynomial, that is beta n into x to the power of n, and the number n we choose depends upon how many unknowns we choose for the dependent variable u. So, we assume dependent variable u bar such a way that the boundary conditions are satisfied exactly. So, we use some functions of this form where alpha 1 and alpha 2 are the unknowns that needs to be determined from the weighted residual technique, and we can see that x into 1 minus x is the first function which goes to 0 both at x equal to 0 and x equal to 1. x square into 1 minus x is again a second function which again goes to 0 at x equal to 0 and x equal to 1. Now we substitute this equation into this equation and we get a residue, and this residue is given by this, which is a function of alpha, alpha 1, alpha 2, which we need to determine. So, we take this residue and weight it with the first function, our first weight function, which is 1. We have used this as the weight function. So, we get this equation. When we weight it with the second function x into this error function, we get the second function. So, we have two unknowns and two equations which can be solved for alpha 1 and alpha 2. If we do that, we get my u bar will be given by this solution. The u exact is given by this. Let us compare. How do we compare? We have to substitute the value of x at some point in both these solutions and find out what is the value of u you get. At x equal to 0.2, u bar is given by this value 0.205 and u exact is given by 0.228. We find that there is 10% error, not a bad thing considering we just considered only 2 terms. So, what happens if we use more terms? Suppose we use our functions as u bar equal to alpha 1 x into 1 minus x plus alpha 2 x square into 1 minus x plus alpha 3 x cube into 1 minus x. Obviously, this error will decrease further. So, if we use more number of terms in the assumed function for the dependent variable, we can improve the solutions considerably. Let us go to the next method, that is the Galerkin method. What is the difference? As we said earlier that in the Galerkin method, the dependent variable and the weight functions are assumed as same. So, here we assume the same variation as we assumed earlier for the dependent variable. That is, we assumed dependent variable of this form and we made sure that this form satisfies the governing equations, satisfies the boundary conditions exactly. That is a fundamental requirement. It has to satisfy the boundary condition exactly. So, instead of using a polynomial form of weight function, we use the same function with b, instead of alpha we attach beta 1 and beta 2 attached to it. So, in Galerkin method, both the weight function as well as the dependent variable variation satisfy the boundary conditions. This is not true in other methods. In other methods, there is no constraint that is placed on the weight function. So, if we substitute this error this function, we get the error function which is of this form into the governing differential equation. Now, we take the two functions, we weight this function with the error function. So, the weight function is exactly same here as we said, the first function is this one. So, we take x into 1 minus x is my first function phi 1, we weight it with this and we get and integrate it, we get an equation in terms of alpha 1 and alpha 2. We take this second function here and substitute it here phi 2 and integrate it, we get the second function. So, while we solve these two functions, there are two simultaneous equations, we get alpha 1 and alpha 2 are given by this and this solution is given by here. So, this solution is vastly different from what we obtained for the method of moments, vastly different. So, we try to substitute at the same point x equal to 0.2 and find out what is the answer for u bar, and we get 0.231 as opposed to 0.228, which is the exact solution. So, we have the error is considerably minimized. What is the reason for getting smaller error here as compared to the method of moments? The major difference is, in the method of moments we used a lower order approximation for weights. Here we use higher order. So, what we used essentially is a cubic approximation, whereas we just use a quadratic approach. So, it is drastically reduced. So, that is expected basically. So, what are the observations that we see? The choice of interpolation function for the dependent variable and the choice of weight functions determines the accuracy of the solution, that we saw in the 3 examples we saw. And we also see that the accuracy can be improved either by using more number of terms or by using higher order approximations, as the case may be. And the higher order approximation depends upon the what is there on the right hand side, the forcing term. Is it going to be a linear force or a quadratic force or a cubic force, etc. And by selecting different forms of weight functions, we can construct new numerical methods. So, that is what we have seen here in this lecture. So, let us summarize what we understood in this lecture. In the last lecture we said what is FEM without giving it the mathematics and science behind the FEM. In this lecture we established the theoretical basis of FEM, and the theoretical basis of FEM is essentially a weighted residual technique. And we also established a direct relationship between the weighted residual technique and the FEM. In weighted residual technique, we take the residue, we force it to 0 in some form, either using Galerkin method or by using least square method or by using Galerkin method. In the FEM, we write the weak form of equation. So, the weak form of equation can be constructed by taking the governing equation and weighting it with the some assumed weighting it with the assumed solution, the governing equations, and integrating over the domain. And while doing that, when we say that the dependent variable is equal to the weight function, we get the the energy functional or the weak form of the equation. So, the minimization of the energy functional is same as obtaining the weight form of the governing equation through weighted residual method. As I said, for FEM we use energy functional, for other numerical method we approach using weighted residual technique. And by using different weight functions we can create a number of different numerical methods. We have seen how we can create the finite difference technique, the method of moments technique, the Galerkin technique, the least square FEM technique, etc. and also the collocation technique. So, we have seen the whole range of different methods, and many more methods can be created by using different weights. So, there is a direct relationship between the weighted residual technique and the finite element technique. Well, the finite element technique uses the minimum potential energy and the weak form. The weighted residual technique goes by writing the by taking the governing equation and weighting it with the some weighted functions. So, here we have established a theoretical basis. In the subsequent classes we will talk about how we can create different elements by taking the physics of the system. Thank you.